Bismillahirrahmanirrahim. Assalamu alaikum students, and welcome to the second part of pre-stressed concrete engineering. In the first part we had discussed the very basics of pre-stressed concrete, but in today's lecture we are going to start discussing the internal stress distribution and the formulation and the method to design pre-stressed concrete beams. Referring to some portions of the previous week's lecture, if you remember, in case of an ordinary reinforced concrete beam which is subjected to dead load and live load, dead load might include superimposed dead load and the self weight as well. There will be strains and stresses developing inside the member, in which the top fibers will experience highest level of compressive strains or compressive stresses, while the bottom surface will observe or will carry the tensile stresses. As concrete is very weak in tension, we used to ignore the tensile capacity of concrete in a cracked section, and the resultant stress diagram would look like this, where compression is at the top above the neutral axis, while below the neutral axis the tensile strength of concrete has been ignored and the resistance from the steel is usually observed. These were two examples of pre-tensioned pre-stressed concrete elements and post-tensioned pre-stressed concrete elements, in which strands or high strength steel wires are passed through concrete, stress is applied on them, which tensile stress on these cables or wires act as compressive axial force or stress on the concrete members, which can balance some portion of the tensile stresses acting below the neutral axis.
Let us consider a simply supported flexural element. The neutral axis can be considered right in the middle. Due to the applied loads and the self-weight of the member, there will be compressive stresses acting above the neutral axis, while tensile stresses will be acting below the neutral axis. The question arises, because concrete is weak in tension, how can we take care of the tensile stresses acting below the neutral axis? One of the methods is to apply axial compressive force on the element. This axial compressive force will generate additional stresses, compressive stresses, to balance the tensile stresses acting below the neutral axis. The pre-stressing force that satisfies the particular conditions of geometry and loading of a given element is determined from the principles of mechanics and of the stress-strain relationships. The similar principles of mechanics which were used in case of ordinary reinforced concrete beam, those principles can be applied to study the internal stress distribution of a pre-stressed beam. Let us consider a pre-stressed beam which is simply supported, and a pre-stressing force P is acting along the neutral axis of the beam. In this particular case, there will be compressive stresses which are generated let's assume the cross section height, this is the width. There will be compressive stresses acting normal to the cross section because of the applied compressive stress P, and that is equal to P divided by the cross-sectional area, where area is equal to this value. Similarly, additional compressive stresses will be generated because of the self-weight of the beam. In this particular case, as we already know, that the stresses generated because of self-weight of a simply supported beam will be compressive at the top and tensile at the bottom. We are using negative sign for compressive stresses while positive sign for the tensile stresses. The value of stresses generated because of the self-weight is mc over I, the moment of inertia. And the resultant of the two type of stresses will be above the neutral axis, the compression from phase 1 and compression from phase 2, they are added, while below the neutral axis, tensile stresses from phase 1 and tensile stresses from phase 2 might get balanced. We can apply the pre-stressing force P in such a way that the tensile stresses may balance each other. So we can say that tension is equal to 0 in the bottom. Now we have solved one of our problem, that was regarding the tensile stresses acting below the neutral axis. Now there are no tensile stresses acting below the neutral axis. But then again we have another problem, that is above the neutral axis. Now we have additional stresses acting, compressive stresses. Although concrete is strong in compression, but while trying to avoid tensile stresses, generating more compressive stresses may not be a good approach. So for solving this problem, we have to modify the location of pre-stressing force slightly. Let's consider a pre-stressed flexural element once again, which is simply supported. The neutral axis passes through the middle, while we can apply the pre-stressing force eccentric to the neutral axis. So we have applied pre-stress force at an eccentricity intentionally. Now the stress condition is different. Phase 1 is similar. Compressive stresses uniform, which are generated because of the pre-stressing force P. Second type of stresses are generated because of the eccentricity of the pre-stressing force P. And in this particular case, we will have tensile stresses at the top and compressive stresses at the bottom. The value can be calculated simply load multiplied by eccentricity multiplied by C divided by moment of inertia I. So these are the two type of stresses generated because of the eccentricity, sorry, the compressive, axial compressive force, and then there is the third stress phase. This one was second. This third stress phase because of the self weight. In this particular case, there will be compressive stresses acting at the top, tensile stresses acting at the bottom, and the value is same as we have discussed already, which is mc over I. And the resultant of these three is a case similar to the previous one, where we have probably tensile stresses reduced to minimum, or we can say zero, while the compression at the top is also minimum as compared to the previous case where the compressive stresses were applied along the neutral axis. So this method of applying axial compressive force at an eccentricity below the neutral axis. Below the neutral axis means that we want to apply these compressive stresses in the zone where tensile stresses would have been developed because of the applied loads, dead load, live load, and the self weight.
So after the brief explanation of the basics, we will move on towards the regular presentation. As already informed that the principle of mechanics and that of stress-strain relationships are applicable to this case as well, so I'm going to skip this explanation for you to read out once again because I have already explained this in the previous slide. Now coming to more refined diagrams. This is the case number 1. P over A is the compressive stress that we actually planned to apply, where the compressive force is acting right along the neutral axis of the member. So because of that, the resultant stress condition before the application of the load, resultant means including the stress generated by because of the axial compressive force and the stresses generated because of the self weight, they are, when combined together, the resultant has zero tensile force but very large compressive force, because compressive stress from stage number 1 and stage number 2, they will be added up together. To resolve this enhanced compression acting above the neutral axis, we can bring the load downwards at an eccentricity as shown in this diagram. So we will get this component PEC over I, additional component, which is because of the negative camber of the beam, which means that the beam will be raised from the middle upward because of the application of compressive force at an eccentricity. So this will help us to balance the additional compressive stresses being generated at the top, while the tensile stresses reduction to zero, that phenomena remains as it is. So this is the resultant. We have already discussed all this in the previous slides. But here we have to, because we have to develop some equations as well to design the pre-stressed members. So remember that the stress generated because of the P compressive axial pre-stressing force is that pre-stressing force divided by the area of concrete, where area of concrete is the whole area, width into the height of the member, and this is compressive. Remember, in all this discussion, negative sign will be used for compression while positive sign will be used for tensile stresses or tensile forces. So this equation 1.2 A and B for top and bottom have already been discussed, where P over A is the component generated because of the axial compressive force, while MC over IG, gross moment of inertia of the section, which in case of a rectangular beam will be equal to BH cube over 12. This equation is 4 combines the stresses because of the axial compressive force and the stresses because of the self weight. Remember one thing, that during design phase, although we are designing at a stage where loads are not being applied, but we cannot ignore the self weight of the member, because it exists all the times after the removal of the formwork. So we have to keep this along with us. Taking it to one step further, I am skipping those explanations because I have explained those things verbally already. Coming to this part, now remember one thing, this is again, we are now moving from equation number 1.2 to equation number 1.3, where we have changed the point of action of the eccentric of the compressive force at an eccentricity equal to E. At an eccentricity equal to E from the center of gravity of the concrete. So this PEC over IG is the additional component developed because of the negative camber. And in this particular case, this component is tensile at the top while compressive at the bottom. So this component will help us balance the additional tensile compressive stresses which were being generated above the neutral axis. In the basic concept method of designing pre-stressed concrete elements, the concrete fiber stresses are directly computed from the external forces applied to the concrete by longitudinal pre-stressing and the external transverse loads. The two equations 1.3a and 1.3b that we have just discussed in the previous slide, these can be modified and simplified for the use in calculating stresses at the initial pre-stressing stage and at the service load levels. For initial pre-stressing stage, we will have the compressive stresses and self-weight acting on the beam, while at service load levels, we will have all three, the compressive stresses, the self-weight, and the externally applied superimposed dead load and live load. All of them might be working together. Let me remind you of one thing that we have already discussed in the last lecture, the effectiveness ratio R. There is another factor, residual pre-stress factor, which is the ratio between effective pre-stress force and the initial pre-stressing force before the stress losses. So this, you have to remember this residual pre-stress factor for the discussions on the during the rest of the lecture. Now this is a simplified form. From equation 1.3, first thing, moment of inertia divided by area of concrete is equal to R square. So we have replaced Ig over AC by R square, or AC over Ig by 1 over R square. So after replacing that, Pi over AC have been taken common from the equation. It is actually the same equation as 1.3a and 1.3b, except this one simplification of R square being which is replacing Ig over AC. So the equation has been slightly modified, or you can say that simplified. Taking it further, if the beam self-weight causes a movement md at the section under consideration, so that self-weight, the stresses because of self-weight can be assumed in the equation. So the remaining portion of equation 1.3 corresponding to the self-weight has been included once again in terms of movement developed because of the self-weight divided by the section modulus. So the component of stress being generated because of self-weight have been modified from mc over I to the moment generated because of self-weight divided by the section modulus. So overall, this equation number 1.3 has been simplified. Now let's move on towards the geometry of the pre-stressing tendons which are passed through a member. There are two ways of doing that. Shape number A or method number A, in which instantaneous change in direction occurs from the midpoint up to the edge, is called halved shape or halved tendon. And if we do it gradually, then that is called a drabbed tendon or a drabbed shape. Because of that eccentricity, quite the stress condition near the edges becomes quite complex, and additional stresses were being generated there. In order to keep the stress distribution under certain limits near the edges, we choose such change in eccentricity during providing the tendons for pre-stressing. So the change in eccentricity from the midpoint to the support, that is used by raising the pre-stressing tendon either abruptly from the midspan, which is called harping, or by gradually in a parabolic form, and that is called dropping of the pre-stressing tendon. Now coming back to the equations, as we already know that there are several types of loads acting on any flexural member. The most important are dead load, superimposed dead load, and live load. The dead load means the self weight of the member, and the moments generated because of the self weight, superimposed dead load, and live load all will act on the member at the service load stage. So if we want to modify that equation 1.5a and 1.5b for the service load stage, so in that case we can simply replace the component of stress which was considered corresponding to the self weight. We can replace it with the component corresponding to the total moment acting on the member. Total moment will include three components. Number one, movement due to self weight. Number two, movement due to superimposed dead load such as flooring. Then number three, movement due to live load. So this is 1.7a and 1.7b equation can be used for the service load stage. Now we are going to discuss a few typical elastic concrete stress distributions. Remember that the concrete girders, pre-stressed girders, are usually not rectangular. Instead, they are flanged from top and bottom. This helps us in a way to avoid using extra amount of concrete which is not required. Increase the amount of concrete at the upper flange region to provide more compressive stress. So in this particular case, there will be two components generated because of the compressive axial force. Pi over AC is the initial pre-stress force divided by the area of concrete to calculate the compressive stresses, while this part B, Pi initial pre-stress force into eccentricity into C over IC is due to the additional eccentric loading, and the resultant can be calculated in this form. Pi over AC can be taken as common, and I over A can be replaced by R square. So the simplified equation is available here for top and for the bottom cases. The same previous equation, when the self weight is included, the equation is modified and the component because of self weight is added in the equations. In the compression side, the sign is negative. For tensile side, the bottom, the sign will be positive. And similarly, in addition to the self weight, moments corresponding to superimposed dead load and live load, the stress generated because of that can also be added for service load stage, and the total stresses at the top and at the bottom during service load can be calculated by using these equations. I am going quickly through these equations because in reality, the way these equations were formed, we have discussed already. I am simply showing you the values once again from the book. A few ACI maximum permissible stresses in concrete. We are going to discuss those. These are very simple things, so I am going to quickly revise them for you. Extreme fiber stress in compression should not be more than 60% of the FCI prime. Extreme fiber stress in tension at the ends of simply supported members should not be more than 6 under root FCI prime. Otherwise, the tensile stresses should be below 3 under root FCI prime. Similarly, the maximum stress limits for service load stage have been given here. For compression, we have 45 to 60% of FC prime, while for tensile zones 6 under root FC prime to 12 under root FC prime. You can go through the details once again for your information. Now we have moved on to design of pre-stressed members. There are a few considerations. Number one, the flexural stresses are the result of external or imposed bending moments, and they control the selection of the geometrical dimensions regardless of the member being pre-tensioned or post-tensioned. Basically, we can choose a geometric shape, and by hit and trial methods we can keep adjusting the shape to suit our requirements. After satisfying the flexural requirements, thereafter other factors like shear and torsion capacity may also be checked, and the sections might be modified to satisfy them as well. As a logical sequence of designing, first of all, the member is designed for service load stage, and after that the limit state at failure, that its analysis is carried out. As explained earlier, negative sign is for compression, positive sign is for tension. A convex or hogging shape indicates negative bending moment, which means tension at the top, compression at the bottom, while concave or sagging shape would denote positive bending moment, as shown in figure 4.1 here. So tensile stresses are at the top, compressive at the bottom for negative bending moment, and its reverse will be true for the positive bending moment. Compression will be denoted by negative sign, while tensile stresses will be denoted by a positive sign. There are various loading stages which are considered during the design phase of pre-stressed member. The first one is initial pre-stress force, which is applied initially. Then at transfer, the force is transmitted from the pre-stressing strands to the concrete. In next step, full self-weight WD acts on the member together with the initial pre-stressing force. Remember that we are assuming a simply supported member. In next step, full superimposed dead load. Self-weight and superimposed dead load both start acting on the member, and most short-term losses in the pre-stressing force occur up to this stage, and the forces are reduced to PE, the effective pre-stress force. Later on, the member is subjected to full service load, where the long-term losses due to creep shrinkage and strand relaxation also occur. Remember that overloading of the member may occur under certain conditions up to the limit state at failure. A typical loading history has been shown in the diagram given on the next slide. Let's move on to that diagram. Loading history. This is point A is the beam cross section. B stress distribution is because of the initial pre-stressing stage and when the tendon is acting at an eccentricity. Stage C, where along with stage B, self-weight is also included, in stage D, along with the A, B and C, the dead load, full dead load plus effective pre-stress is considered. Full service load has been considered in stage E, where the bottom members start showing some tensile stresses. And stage F is the limit state for the member. This is a typical load deformation curve of a pre-stressed member. This initial portion is quite interesting because of the applied initial pre-stress force. At initial stages, we have this shift from hogging to sagging. So that is why it seems as if the deflection is returning, because initially the member should have hogging, the negative movements. Later on applying more load, it keeps on shifting from sagging to hogging. This is the neutral stage, and afterwards it gets to the peak, the ultimate stage where the concrete ruptures. We will discuss the detailed shape in the class later on. Selection of geometrical properties. General guidelines include: number 1, under service load conditions, the beam is assumed to be homogeneous and elastic. The reason to assume this elasticity is, we have actually discussed this elasticity already, and one more concept related to elasticity, that was the cracks are usually recovered, they closes because of their compressive stress when the externally applied live loads are removed. So for that reason we can assume this beam as elastic. Stress analysis of pre-stressed beams under these conditions is no different than that of a steel beam or a beam column. More accurately we can say a beam column. Remember that axial force will always be present whether superimposed dead load, live load is acting or it is not acting. As discussed earlier, the pre-stressing tendon profile should be eccentric at critical sections, for example, the mid-span. Instead of a rectangular solid cross-section, a non-symmetrical flanged section is preferable to avoid using additional concrete and providing more concrete as required at the upper portion above the neutral axis where compressive stresses are dominant. After selecting a shape, a general shape, we have to begin with calculating section modulus, minimum section modulus at top fiber and at the bottom fiber, but after checking the limiting stresses given by the ACI code, which was 60% of FCI prime, 300 FCI or 600 FCI, or in case of service load stage 45% or 60% of FCI, FC prime, or 600 FC prime to 1200 FC prime. So after checking these limits, then we can proceed towards calculation of the section modulus and other steps of designing a pre-stressed member. So these equations can be used to calculate effective stresses after the losses and at service load stage. After losses would include the stresses because of pre-stressing force and self-weight, while at service load stage the stresses will include pre-stress force, self-weight, superimposed dead load, live load. In fact, all type of movements being generated, being acting on the member. So the first two equations are for stress condition determination at top and bottom at the time of initial pre-stress, and this is the last two equations are the stress conditions at top and bottom during the service load final stages. If these slides are not properly visible, you can refer to the PDF notes which has been uploaded on LMS. As discussed earlier, the total movement will include all the movements, especially the movements generated because of self-weight, superimposed dead load, or the live load. At the end of the lecture, we have one simple example to solve. Let me go through the problem statement. A pre-tensioned, simply supported double T beam without topping means no flooring, no superimposed dead load at this stage, has a span of 64 feet. And the geometry shown in the figure will be on the next slide. It is subjected to a uniform superimposed gravity dead load and live load. The total superimposed dead load and live load are 420 pound per foot, or you can assume 6.13 kilonewtons per meter. The initial pre-stress force before the losses is 70% of the ultimate stress, which is 189,000 psi or 1303 megapascals. The effective pre-stress after losses can be considered 150,000 psi or 1034 megapascals. We are required to compute the extreme fiber stresses at the midspan due to the initial full pre-stress when no external gravity load is acting, the final service load conditions when pre-stress losses have taken place. So actually the same two type of stresses at top and bottom are to be calculated for initial full pre-stress stage and the final service load stage. A few values corresponding to the section have been given. C value for bottom and top are 452 millimeters and 158 millimeters respectively. The eccentricity values have also been given. Section modulus for top and bottom have also been given, and the self-weight value as 4.45 kilonewtons per meter has also been given. Remember that in these slides the values will be calculated in this FPS system, but you can use the other values to confirm the values or to calculate the values in the SI system. This is the full profile. 64 feet long girder is there. This is the halved profile for a tendon. The superimposed dead load, live load together are equal to 420 pounds per feet. This is the cross section, double I section for the girder. The cross-sectional dimensions have been given so that if needed, cross-sectional area or other cross-sectional properties can be calculated from this cross-section. However, in this particular example, these values have been given already, where area of concrete is 449 square inches, while the moment of inertia for this given shape is 22469 inch raised to power 4. Some stress values have already been given. Fc prime is 6000 psi. The specified tensile strength of the tendons is 270,000 psi. The specified yield strength of the tendons is 220,000 psi, while the effective pre-stress force, which was also given in the statement, was 150,000 psi. Remember that these are not decimal points, these are the commas, like in this case. The limiting values are 12 under root Fc prime for maximum allowable tensile stress in concrete, 0.6 Fci prime for maximum allowable stress in concrete at initial pre-stress, 0.45 Fc prime for maximum allowable compressive stress in concrete at the service life stage. After we have assumed these values, we can move on forward with the solution. These were the cross-sectional properties given in the problem statement, so I do not need to repeat them. As we know that in the formula to calculate stress at the top or bottom, we need to know the total pre-stressing force, the maximum pre-stressing force that can be applied to the member. For that, we need to calculate the area of pre-stressing strands. We have assumed the number of strands being 10, area of one strand as 0.153 square inches. So the total area of pre-stressing strands, or total area of steel in the pre-stressing strand, is 1.53 inch square. For initial pre-stress force, area multiplied by the initial pre-stress that can be used, area of pre-stressing force can be taken from this formula above, while initial pre-stress force was given in the problem statement, which was equal to 189,000 psi. Similarly, effective pre-stress force can be calculated as area of pre-stressing strands multiplied by the effective pre-stress, maximum effective allowable pre-stress, which was 150,000 psi, given in the problem statement on third slide of the problem statement. The dead load has already been given, 359 pound per foot, and we know that in case of simply supported beam, the maximum bending moment at the center point, middle of the beam, can be calculated by using the formula WL square by 8. So the same formula have been used to calculate the moment. This 12 would convert the 64 feet to inches, so that we can have moment calculated in inch pound. Corresponding moment in SI system will be 249 kilonewton meters. So now we have calculated the moment because of the self weight, and we have the initial and effective pre-stress force acting on the strands. To calculate stress at the top, the formula, as we had already derived, is minus PI, effective pre-stress force, divided by area of concrete, into 1 minus E C top over R square, minus moment because of the self weight divided by section modulus at top. All the values required in this formula have already been calculated, so you can simply input the values and calculate the final results. As I cannot calculate the final results on these online lectures in front of you on the board, so you are required to carry out all the calculations for this example either in the FPS system or in the SI system, and later on we can compare the results. These are the stresses at the top, and similarly for stresses at the bottom, the major difference is only the sign and the section modulus and the corresponding C value for bottom. So in case of the stresses generated because of at initial pre-stress stage, the moments generated because of self weight will be assumed alone, while for final condition at the service load stage, we have to calculate the moment WL square by 8 because of the total superimposed dead load and live load, and these need to be added to the moments generated because of the self weight. So total moments can be calculated, and they will be used in the formula for stresses at the top and stresses at the bottom. Remaining formula is same as in the previous case, so I do not need to explain that. And these values should be calculated against the limiting values for initial pre-stress stage and the final service loads conditions. And the current conditions should be lesser than the maximum allowed limits. So for top and bottom, the values have been calculated. 45% of the FC prime is the limiting value for the compressive stresses at the top, while 12 underroot FC prime for the tensile stresses at the bottom. And in the given example, both of these values are satisfied. Once again, I am telling you that because I cannot solve the problems similar to the way I would have solved on the board with you guys in the class, so you are required to solve these problems on your own. Write down your questions and queries that you will get during solving the problems. Definitely you will have a lot of questions. We are going to discuss all those questions during our online lecture this week. With this, I would like to end today's lecture. Thank you very much for your concentration in the lecture. Allah Hafiz.